In this video, we're going to walk through the solution for another example of the Nerst equation. We've been given a redox reaction at 25 degrees Celsius, but it's not at standard conditions. Rather than 1 molar solution concentration, we have 0.1 molar for all of our reactants. And we need to calculate the cell potential. So the reactions that we're going to use are over here. We have to figure out our standard cell potential, and then we can use the Nerst equation to solve for our actual cell potential. I've gone ahead and I've separated out our reduction and oxidation, set up both of our half reactions, and given the reduction cell potential for each of them from our standard reduction potential chart. And so looking at this equation, I want to highlight our iodine reaction right here with the iodide. So this is actually the reaction that's being oxidized. And I've written it here as a reduction for the reduction potential. But this is what's going to take place at our anode. Whereas our IO3 becoming our I2 is going to happen at our cathode. So when we want to calculate our cell potential for standard cell potential, we're going to set this up as our cathode minus our anode. Using just reduction potentials. So this is going to be equal to our cathode's reduction potential, which is 1.20 volts, minus our anode's reduction potential, which is plus 0.54 volts. That's going to give me a standard cell potential equal to 0.66 volts. And that's going to be the value that I plug in for my cell potential in the Nerst equation. Now I'm going to look at the number of electrons, so N. So looking at my two half reactions, I can see that my oxidation reaction or my iodine's reaction is only 2 electrons, whereas I have 5 electrons for my iodate reaction. So I'm going to multiply this reaction, the iodate reaction, by 2. So that way I end up with 10 electrons. And I would also end up with 6 waters, and I would end up with 1 iodine, and I would end up with 12 H pluses and 2 iodates. And then I am going to, wrong color, do the same for my iodine reaction, except I'm going to multiply it by 5, so that way I end up with 10 electrons. I'll also end up with 5 iodines, and I'll end up with 10 iodides. So now I can see that my N value is going to be 10 for my 10 moles of electrons. So I'll highlight that. That's going to get plugged in as well into the Nerst equation, which leaves me just one more value to calculate. And that is going to be Q, which is going to be the reaction quotient for the reaction. And so I'm going to focus on my total equation rather than my half equations for my Q value. Remember, this is always going to be equal to products over reactants, but we're going to make sure everything is in the aqueous state. So looking at my products, I have iodine and water. Both of them are either solid or liquid, not an aqueous or a gas. And so there actually isn't a product that is included in my reaction quotient calculation. So I'm just going to put a 1. And then I've got a lot on my reactant side. So I've got my iodate, my IO3 minus, and I've got 2 of those, so it's squared. I'm going to multiply that by my H plus concentration to the power of 12, because I have 12 of them for my coefficient. And then I'm going to multiply that by my I minus, and I'm going to put that to the exponent of 10, because I have 10 of them, which is pretty big. So that's going to be equal to 1. And then all of these are a 0.1 molar concentration. So it's 0.1 squared, 0.1 to the power of 12 times 0.1 to the power of 10. Plugging that into my calculator gives me a value that I didn't actually calculate. So I'll pause for one quick second. All right, this gives me a value of 1 times 10 to the negative 24th, which I guess I could have done in my head, but I didn't. So that's going to be that Q value right here. And so now my job is just to plug everything into the Nerst equation. So that cell potential is going to be equal to the standard cell potential, which I calculated to be 0.66 volts, minus that 0.0592 volts, which is that sum of so many constants altogether, divided by our 10 moles of electrons, then times the log of 1 times 10 to the negative 24th. Now, all of that, when I plug it in, is going to be equal to 0.52 volts. And that is going to be my cell potential right there for this reaction at non-standard conditions.